if we're going to graph polar equations, it's going to help a lot if we can classify them. So let's look at the different types that we're going to have. We're going to see some circles. And something called lemniscates. Lemniscates kind of look like bow ties. But I guess you need to pay attention to the equations. That's how you're going to tell. And so a circle might look like this. It might look like r equals 2 cosine theta. Or r equals 3 sine theta. And pretty much, as a general rule, if you see cosine, it's going to be oriented on the x-axis. Now, that doesn't always make the case for the y-axis, but what will always happen is if you see a sine, it will not be on the x-axis. So your rule is if you see cosine, it's going to be on the x-axis. Some part of it's going to be on the x-axis. So this lemniscate over here might look like r squared equals 9 sine 2 theta. Or sometimes you'll see it if they square root both sides, be plus or minus square root of 9 sine 2 theta. Something like that. And so then this other one, r squared equals 4 cosine 2 theta. Again, if you see that cosine, you're going to see something lying on the x-axis. Okay? You know, cosine goes with x, sine goes with y. So then the next set would be the limicons. Limicons, there are 3 different types of limicons. This limicon over here is with inner loop. Okay, you see this part right here is what we're calling an inner loop. This one, the second one, is a special one called a cardioid. And a cardioid, cardio meaning heart, they're saying this kind of looks like a heart. But a cardioid, what's special about this is it touches the origin right there. Okay? So the others are just regular limicons, and you might say without inner loop. They all kind of look the same, and their equations are going to look like this. You're going to have either this form or this form, but the numbers are what is really going to make the difference. So with inner loop, you're going to see something that looks like this. R equals 1 plus 2 sine theta. Cardioid might look like R equals 2 plus 2 cosine theta. Without inner loop, you might have something in the x direction like R equals 3 plus 2 cosine theta, or something in the y direction, R equals 5 plus 2 sine theta. You want to pay attention to the numbers. And the cardioid is the easiest one to pick out because those two numbers will be equal. If those two numbers are equal, it's going to be a cardioid. If this number is bigger than this number, it's going to have an inner loop. Okay? Otherwise, if this second number is smaller than the first number, it's not going to have an inner loop. So those are the limicons. So we've got circles and lemniscates and limicons and roses. Roses. You want to pay attention to the number of petals this time. If we've got something that looks like r equals 3 sine 2 theta, or here's r equals 5 cosine 4 theta, r equals 4 cosine 3 theta, r equals 7 sine 5 theta. What you should pay attention to, I guess, is this number. If this number is even, we're going to have double that number of petals, of rose petals. However, if that number in front of the theta is odd, it's just going to be that number of petals. So it really, really helps to be able to classify these things. Just know what you're looking at before you even start. So some quick examples. Okay, let's try to match them up. You've got circles, lines, spiral, limison, cardioid with inner loop, limit, and rows. Okay, so let's look at this one. I recognize that it's one of the three limisons because it has that plus sign in it. Okay, but what you'd be looking at is that 5. That number 5 is bigger than the number 4, and so that's going to make it a limison with inner loop. I can also tell because of that cosine which direction it's going to be pointing. It's going to be pointing in that x direction. Okay. I didn't show you one of these, but r equals 2 theta is going to be a spiral. 4 cosine theta. 4 cosine theta. Oh wait, no, that's not 4 cosine theta. That would be a big difference. Okay, you notice these two look kind of the same. One of them is a circle and one of them is a rose. The one with just theta by itself is going to be the circle. The one with the 2 in front of it is going to be a rose. And not only is it a rose, I can tell because of that 2 that it's going to have twice that many petals. It's going to have 4 petals. This next one right here, again, I see that plus sign. That plus sign is going to tell me that it's going to be a limison. But when you notice those 2 5s, and those 2 5s are the same, that's going to be a cardioid. This one, r squared equals 9 cosine 2 theta. Okay, this is the only one with r squared in it. Or, sometimes you might end up taking the square root of both sides. So if you ever saw a square root, it'd be kind of the same indicator. But as is with this r squared, that's going to be the limit state. 3 plus cosine theta. Again, the plus sign is your indicator. But since this number in the front of the cosine is 1, and that's smaller than the 3, I know that's going to be a limison with no inner loop. Okay? The last two I didn't show you an example of. R equals 4 should be easy to figure out if you know that R stands for radius. Basically, this says radius of 4. That's another circle. Okay? That's another way of writing a circle, R equals 4. And then this is the only one that's weird. Something that looks like this, 2 over cosine theta plus sine theta. That's going to be a line. So you need to be able to classify these. As soon as you classify these, the graphing is going to become a million times easier. 8.7, we're doing polar equations and graphs. And it's kind of like when we deal with rectangular, when we deal with polar, it's kind of like that's 2 sides of the same coin. I realize we are very comfortable with rectangular. If I gave you the point 3, 5, I think everybody in here would know to go right 3 and up 5, and that's where that point would be. Okay, we're good at that because we've spent years talking about the rectangular coordinate system, x and y. But polar is just the other side of the same coin. We're still describing some place. Okay? So if I gave you like 5, 45 degrees, that's just describing a point in the plane somewhere. Okay? I guess the main difference is you want to find the angle first. Imagine if somebody told you to walk a mile north. You don't just start walking a mile. You'd have to point yourself in the northerly direction first, find the direction first, and then walk a mile. So when you're looking at a point in polar coordinates, you're going to want to find the angle first, 45 degrees first, and then go 5 in that direction. That's how it's going to work, though. One of the things we'll have to do is convert back and forth, and you should be familiar with this because we've done it the past 3 or 4 lessons. So we use these formulas. Now notice I added this extra one. Actually, this is the one we're probably more used to, and we might need to use the cousin of this. These two are cousins. But look at these 5 formulas. These 5 formulas are ones we would use to go back and forth. Those should look familiar to you. Example 1, we're going to plot some points. It says plot each point by hand, then determine the rectangular coordinates of each point. So in order to plot this by hand, it's really pretty simple. Start with 30 degrees, though. Now, it would be nice if they labeled it, but they didn't label. This is 0 degrees, and we know this is 90 degrees. It turns out that every one of these marks goes by 15. So that's 15, 30, 45, 60, 75. We could go all the way around the circle if we want. I don't really want to, though, because we don't need to, because we're looking at 30 degrees. And so the first thing you would do is find the mark that coincides with 30 degrees, and then go 2 units in that direction. So did you find the mark that corresponds with the 30? Start from the origin, and go 2 in that direction. 1, 2, there'd be a point right there. So 30-degree direction, 2 units in that direction. That is point P. So let's label that point P. That's all there is to it for graphing. But then notice it says to determine the rectangular coordinates. Anytime they say that, they're talking about x and y. And we know how to do this because we've done it the last couple of sections. If I want to find the x part, I'll take 2 cosine 30 degrees. So use the chart. Cosine 30 is what? Square root of 3 over 2. Good. So we have 2 times square root of 3 over 2 is just square root of 3. That's the x part. And then if I want to find the y part, it's going to be 2 sine 30. Yes. What's sine 30? 1/2. Very good. 2 times 1/2 is 1, and that's your y coordinate. So if we were writing the rectangular coordinates, you could write it as a point, I suppose, square root of 3 comma 1, or you could write it as a vector like we did in the last section, square root of 3 plus I, one way or the other. Either way, that's describing the same location. One B, you've got another pair of points, but this one's in polar form. Right? I mean in radians. Okay, it's polar form, but it's in radians. And so here's 0 and here's pi over 2. I always start with that. Now, one thing to keep in mind, or one thing to know, I guess, is 15 degrees is the same thing as pi over 12. So every one of those marks is 15 degrees, it's pi over 12. So this is pi over 12. 2 pi over 12 reduces to pi over 6. And 3 pi over 12 reduces to pi over 4. And 4 pi over 12 reduces to pi over 3. And 5 pi over 12 doesn't reduce. And then 6 pi over 12 is pi over 2. And so I'd probably start with that in radians. Now notice we have to go to 2 pi over 3. So really we could keep going, another pi over 12, another pi over 12, another pi over 12. Or here's a shortcut. See how this is pi over 3? Here we go, 1, 2, 3, 4 marks is pi over 3. So 1, 2, 3, 4 more marks will be another pi over 3. And so 4 more marks is where 2 pi over 3 would be. I don't have to label everything. I just need to find where 2 pi over 3 would be. And that's the direction of 2 pi over 3. Now, notice this negative 4. This negative 4 just means the opposite direction. Okay? The opposite direction. And so really what we would do is we would identify the direction of 2 pi over 3, but we would go in the opposite direction. So count off 4 in the opposite direction, and that's where point Q would be. Now I'm going to skip the conversion. Well, let's do the conversion. The x would be negative 4 cosine 2 pi over 3. And so in order to do cosine 2 pi over 3, look at its reference. It's a cosine pi over 3, but it's in the second quadrant. Cosine pi over 3 is 1/2. In the second quadrant, that makes it negative. So we've got negative 4 times negative 1/2 is positive 2. And then when y equals negative 4 sine 2 pi over 3. Sine 2 pi over 3 is like sine pi over 3 in the second quadrant. So sine pi over 3 is square root of 3 over 2. In the second quadrant, it's still going to be positive. So negative 4 times square root of 3 over 2, that's negative 2 square root of 3. Negative 2 square root of 3. So your rectangular coordinate is going to look like 2 comma negative 2 square root of 3. Part C, we've got 5 comma negative pi over 4. So pi over 4 is up here. That's like 45 degrees. Negative pi over 4 must be down here. So again, start with the angle. Start with that direction. negative pi over 4, and then go 5 units in that direction. So 1, 2, 3, 4, 5 puts us right there. That's point R. I'm going to skip the conversion on this. Now, notice one thing that makes this, I don't know if it makes it harder or easier, but basically there's an infinite number of equivalent points in polar form. If I'm in rectangular and we go over 3 and up 5, that's it. That's the only way to represent a point in rectangular. But in polar form, you think about it, all I'd have to do is add 360 degrees and I'd be right back at the same place. Add 360, add 360, add 360. There are going to be an infinite number of different ways of representing a point in polar form. Example 2, give 3 other pairs of polar coordinates for the point P, which is 3, 140 degrees. All right, so I think the most obvious thing is to add 360 degrees. So one thing you can do is let's just add 360. So another way of representing this would be 3, 500 degrees. Okay? That's the same place. Add 360, add 360, add 360. I could do that an infinite number of times and get an infinite number of different representations for that same location. Okay? But that's too simple. Let's visualize where this is. 140 degrees puts us, I don't know, about there. So let's say that's a distance of 3 at an angle of 140 degrees. So this is the point 3, 140. Think about other ways of representing this point. Okay? One thing we could do is go around backwards. If I went around backwards, that's 180 plus some more. That's a 40-degree reference, by the way. What is that angle if I go around backwards? Negative 220. That's a negative 220-degree angle. And so another way of representing this point would be 3, negative 220 degrees. Okay. Let's see, what else could I do? I guess I could think about kind of the anti-point, I guess, right here. If you go, what would that be? 40-degree reference all the way around except for that 40, that's 320 degrees. If you went around 320 degrees, you'd be at this point. And so what I could do is say, go 3 in the opposite direction from 320 degrees. I kind of don't like that way, but that'll work. And of course, you can always just add 360, add 360, add 360. So you have 3 other pairs of polar coordinates. Got it. All right. Part B. Determine 2 pairs of polar coordinates for the point with the rectangular coordinates negative 1, 1. We've been doing this for the last couple of lessons. You have to recognize that when they say they want polar, that means they want r and theta. And when they say we have rectangular, that means we have x and y. And so we're using those formulas to go back and forth. We're taking our x and our y and we're changing it into r and theta. We want polar, so we want direction and magnitude. So let's start with magnitude. We know the formula looks like this. We've used it for the last 3 lessons. So square root of negative 1 squared plus 1 squared, that's square root of 1 plus 1 or square root of 2. That's the magnitude, the r value. As for my direction, tangent theta equals y over x. Or in this case, tangent theta equals 1 over negative 1. You want to be able to use the chart and find what angle is going to give us a tangent value of 1 over 1. Okay? You guys see how that's going to be 45 degrees? That's going to be a 45. Now, that's not the answer. Negative 45 is not the answer. We're talking about a 45-degree reference where tangent is negative. And so think about where that is. Tangent is negative in quadrant 2 and 4. However, we know where we are. The point is at negative 1, 1. Negative 1 comma 1 puts us in which quadrant? Left 1, up 1 puts us in the second quadrant. And so what we're really looking at is a 45-degree reference in that second quadrant. What angle are we talking about? 135, very good. 180 minus 45 is 135. And so I've got my magnitude and I've got my direction. That should be enough for polar coordinates. Polar coordinates is going to be square root of 2, comma, 135. Okay, example 3, for each rectangular equation, give the equivalent polar equation and sketch its graph. So notice how they're giving it to us in rectangular, which means x and y, but they want polar, which means r and theta. It's the same thing as what we've been doing. They're wanting us to convert. Okay? They're wanting us to convert. I want to be able to see polar. And so if you think about the conversion, I know that y is equivalent to r sine theta. And I know that x is equivalent to r cosine theta. So I just do a conversion. I use the same exact formulas that I've been using, but I do a conversion so that I can see an r and a theta. Now, if I wanted to graph those, I'm going to need to isolate the r. If you wanted to plug that in on your calculators, you'd want to isolate r. And so that's what we'll do. We would subtract this over so we can get the r's at least on the same side. We have r sine theta minus r cosine theta equals negative 3. You have to do a little bit of factoring. I see both of those expressions right there have an r in it. So it's like we take a GCF, a common factor of r, out. And that's really the hard part, I think. That's the trick to this. Factor out r so you can get it iso. We've got r by itself now. Well, I guess if I divide both sides by this, I will. We're going to divide both sides by sine theta minus cosine theta. So r will equal negative 3 over sine theta minus cosine theta. Give the equivalent polar equation. Good, got it. And sketch its graph. So let's use the calculator to sketch its graph. Go to Desmos. We want r equals negative 3 divided by cosine theta minus sine theta. So you can see it's a line. We knew it was a line. Remember, if you look at the original equation, it said y equals x minus 3. Y equals x minus 3. Oh, wait a minute. I didn't type that in right, did I? It's sine, is it sine theta minus cosine theta? Is that the same thing? Oh. That'll do it. Okay. That looks a lot more like what I wanted. I wanted something that looked like x minus 3. If you think about what we would have done in Algebra 1 class, start at negative 3, go up 1 over 1, up 1 over 1. That's what this is going to look like. So maybe I zoom in and look for intercepts. I think the easiest way to graph this is going to be to look for intercepts. But I can see that it crosses at negative 3 on the y-axis and negative 3 on the x-axis. Or, really, you can't really say about x and y. You'd be looking at a distance of 3 at 0 degrees and a distance of 3 at 270 degrees. So it's going to have a point at 3, 0, and a point at 3, 270. It's going to be a line through there. Let's go ahead and look at part B. Part B, we're doing the same thing. Well, notice x squared plus y squared. X squared plus y squared is equal to r squared. We've got a formula for that. So r squared equals 4. If you took the square root of both sides, you're going to get to r equals 2. You can say plus or minus, but the minus doesn't totally make sense here when we're talking about a radius. Okay? This says radius equals 2. What's that shape? It's a circle. That's a circle with radius 2. And so a circle is really easy to draw with this paper. Just trace a circle with radius 2. And that's it. Example 4. Graph r equals 1 plus cosine theta. The best thing that you can do when you're graphing one of these is just know what it looks like ahead of time. And you should be able to recognize, because of that plus sign, that it's going to be a limit sign. Okay? But specifically, when this number 1 matches this number 1, we know it's a special kind of limit sign called a cardioid. So if you had something like r equals 3 plus 3 cosine theta, same thing. Maybe that would make it more obvious that those two numbers match. But anytime those two numbers match, it's going to be a cardioid. Okay? Cardioid. Cardio. Think about a heart. It's going to look kind of like a heart. But what you're looking at is you're looking at this cosine, which has something to do with the x direction. And so I know that that heart is going to be pointing in the x direction. So it's going to look something like this, I suppose. Okay? We already kind of know what it looks like in advance, and that's the best thing that you can do. Memorize that pattern. It's going to make a cardioid. The cosine is pointing us in the to the right. So if you didn't have any kind of graphing software, you'd make a table, and you might start with something easy like 0. You would have 1 plus cosine of 0 degrees. Now cosine 0 is equal to 1, so we'd have 1 plus 1 is 2. I would have to graph the point 2, 0. And so go in the direction of 0 degrees, go over 2. You'd have a point right there. 2, 0. Okay? So another easy number to plug in would be 90 degrees. 90 degrees. You have 1 plus cosine 90 degrees. And cosine 90 is 0. 1 plus 0 is 1. And so we've got the point 1, 90. So go in the direction of 90 degrees, go up 1. And there's another dot. So you can continue this and keep plugging numbers in. Maybe we try something else easy, 180. 1 plus cosine 180. Cosine 180. And where 180 is, right here. Sometimes people struggle with 180, but that's a 0 degree reference. So it's kind of like we're doing cosine 0, but it's over here. And we know numbers are negative over here. Cosine numbers are negative over here. So cosine 0 is 1, but on that left side, that's going to be negative. So negative 1. We'd have 1 plus negative 1 is 0, and so I've got the point 0, 180. 0, 180 is just, I guess, right there. And so then maybe I do another point, maybe I do 270 degrees. 1 plus cosine 270. Cosine 270 is 0, 1 plus 0 is 1. I've got the point 1, 270. So go in that 270 direction, go down 1. That's, maybe that's enough dots, especially if you know what a cardioid looks like. You know what a cardioid looks like, that's going to something like this. Okay? So you look at that graph, and it definitely looks like a heart. You can see why they call it a cardioid. Now, if you want to, you can change the scale. And let's say we go by, let's go by 5s maybe. 1, 2, 3, 4, 5. Let's say every 5 is 1. And so if we did that, you 2 and you 1 and you 0 and you 1, maybe you blow it up like that. Maybe it looks nicer. It's easier to see your cardioid. So there it is with the change of scale. If you don't like that, then don't change your scale. You can make a tiny one. It doesn't really matter. Either way, there's your cardioid. Example 5, we're going to graph. And honestly, if you want to be good at this, you want to know what it looks like before you even start. So look at your equation, and hopefully you can classify this as a rose. Okay? The dead giveaway, I think, is this 2 right there. Because if that 2 wasn't there, if you had just 3 cosine theta, you know what that would be? That would be a circle. Okay? But with the 2 in there, we know it's a rose. And so we just look at this equation and we know several things about it. Number 1, we know it's a rose. But the fact that it has a cosine in it tells me which direction it's oriented. Namely, the cosine has something to do with the x-axis. I know that part of this rose is going to lie on the x-axis, but this 2 also tells me how many petals there are on this rose. How many petals are there? 4. Good. We talked about the generalization, the general rule yesterday. If this number is even, what's that mean? It's double that number of petals. So I'm going to have 4 rose petals. It's a rose located on the x-axis. There are 4 petals. Oh yeah, and this number 3 tells me about the size. Okay. So when I graph this, basically I would know that I can go out 3 right here on that x-axis. And I'm going to have one of my 4 flower petals, or rose petals, is going to go out like that. Okay? So because this has symmetry, I can go out here, there's another one. And 1, 2, 3, and 1, 2, 3. And it's going to look something like this. So I've got a 4-petal rose oriented on the x-axis with that magnitude of 3. Now, if that's not good enough for you, you can check out a graphing resource like Desmos. Let's see what that gives us. Okay, now what did I do wrong? I forgot the 2. So without that 2, it's a circle. So put the 2 in. That's what makes it a rose, right? Okay, so we put a 2 in. And you can see that it's going over to 3 right here, and it's going up to 3, and over to 3, and over to 3. So we can see exactly what it looks like, or a better representation of what it looks like. Better than maybe what we can draw. But it's the same thing. You've got a rose with 4 petals. Looks something like that. Now, if you wanted to change the scale on your graph, you could. Maybe we make every 3 marks equal to 1. We can always change our scale. And so then we'd have over here is 3, and over here is 3, and up here is 3, and down here is 3. Maybe you want to change your scale, make it look bigger, make it easier to see what's going on. Or maybe you don't. You can just leave it like that if you want. Number 6, I can tell by looking, is a limit scale. Okay? And your indicator is going to be when you see r squared equals, or if you see r equals square root, something like that. But that's what you're looking for. That's how you would know it's going to be a limit scale. And so in order to graph this, I would maybe isolate the r. You take r, square root of both sides, you're going to end up with plus or minus square root of cosine 2 theta. And if I didn't have any graphing software, I would make a table, but this is going to be pretty difficult to do. I'd try 0 degrees, and I'd have plus or minus square root of cosine 2 times 0 is 0. And so cosine 0 is 1. I have plus or minus square root of 1, so plus or minus 1. And so if you go to 0 degrees, basically this represents 2 different points. You have 1, 0, and you have negative 1, 0. And so if you look at 1, 0 is going to be right there, obviously, but negative 1, 0. Go in the 0 direction, but go negative 1 or go the opposite direction. You've got this. Okay. You know, you can start plugging in other stuff. You can try 15. You can try 30. But it's going to be really difficult to graph this. Okay. I know what this one looks like because I've seen them before, and I've got the pattern memorized. It's going to look like this. It kind of looks like an infinity symbol. But you know what you should really probably do is go to a graphing software and just type it in. SQRT is square root. Square root cosine theta. Okay. And maybe zoom in. There you've got a pretty good idea of what this looks like. Looks like an infinity symbol, kind of. Looks like a propeller or a bow tie. That's what that looks like. If you want to change the scale, maybe that's a good idea. Change the scale, 1, 2, 3, 4, 5. Maybe every 5 represents 1. And so we can maybe draw a little bit better one if we change that scale. There is your limit scale. When I look at example 7, I immediately know it's going to be a spiral. Okay, the spiral is really, really hard to graph using a table. Suppose you could use a table. You start plugging in whatever you want. You can plug in 0, you can plug in 15, you can plug in 30. You can plug in anything you want, but I think it's going to take you forever to really get a feel for what this graph looks like. So let's just go to Desmos again, and let's see what this looks like. It was r equals 2 theta in radians. Thank you. Okay, so notice, I mean, you really need to zoom out to be able to see what actually happens here. So it's kind of hard to tell, but 1, 2, 3, 4, 5, 6. It goes around like 6 times there. So, you know, are you going to be able to draw this? I don't know how accurate I'm going to force you to be, but let's just draw kind of a quick sketch, I suppose. But notice we have to go out to like 100, so let's change the scale. Okay, let's change the scale, and then we're going to go around 1, 2, 3, 4, 5, 6. That's not perfect. That's not perfect by any stretch, but I mean that's pretty much, you know, that's a decent indication of what it looks like. Okay, feel free to take your time and do a little bit better job, but I'm not going to force you to be super accurate on that. Okay, let's look at number 8. Okay, number 8. I bet you don't know what that looks like. Okay. They want us to convert it to rectangular. So every time they ask us to convert to rectangular, they're talking about x and y. So they want x's and y's instead of r's and thetas. Let's just type that in and see what it looks like first, though. 4 over 1 plus sine theta. Looks like a parabola, right? Looks like a parabola. And you can zoom in and you can tell that it has a vertex up here at 2, and it looks like it crosses at 4. So those are kind of its points of interest, I suppose. So it has a vertex at 2 and 1, 2, 3, 4. 1, 2, 3, 4. I can already tell pretty much what it looks like. Looks like a parabola. But they want us to convert, so let's convert. Okay. Basically what we would do here is we're looking for some way of changing into x and y. And so as you examine this equation, you see an r and you see a sine theta. Now they're not written together, but if you could piece them together, r sine theta would look like y. That's one of our conversion equations, so that would be useful if we could get r sine theta out of that somehow. Okay? And so I figure what we can do is if we look at this as a proportion and kind of cross multiply, we're going to end up getting an r sine theta. So imagine if we cross multiplied that, you'd have r times 1 plus sine theta equals 1 times 4. Okay. Distributive property, I'd have r plus r sine theta equals 4. So I can convert now because I know that r sine theta is equal to y. So I know that would equal y. I can do my conversion on that. But I've got another conversion for r because I know r equals the square root of x squared plus y squared. So we've got a couple of conversions we can do. And I know that second one, this one's kind of ugly. But we have the square root of x squared plus y squared plus y equals 4. At which point we really want the square root to go away. And so what I would do is isolate my square root. I'm going to subtract this y over. X square root of x squared plus y squared equals 4 minus y. And I can isolate the square root. I can square both sides to make it go away. So squaring both sides, I've got x squared plus y squared equals, and I'm not gonna FOIL that out. I would just leave it as 4 minus y squared. Actually, let's go ahead and FOIL that out. That's going to be 16 minus 8y plus y squared. Once you FOIL that out. So we have x squared plus y squared equals that. And you would notice those y squared would cancel each other out. X squared equals 16 minus 8y. Or switch that around, x squared equals negative 8y plus 16. You're starting to look like an equation of a parabola. Okay, remember from Algebra 1 class, it always said y equals something x squared. That was always a parabola. Now this isn't quite written in that same form, but maybe from Algebra 2 or maybe from your college algebra class, maybe it was written in this form. But maybe if we factor out that negative 8, it looks even more so. If I factor out a negative 8, I would have x squared equals negative 8 times the quantity y minus 2. And so you can see from this equation, you can see the negative sign indicates it's pointing down. This x squared indicates that it's a parabola. The negative that it points down. And here you've got the 2 part of your vertex. And so, remember in vertex form, actually that wouldn't be over there, it'd be over here. It's like over here is x minus 0 squared. And so you can kind of see your vertex of your parabola. We're seeing a parabola that opens down, and we see a vertex of 0, 2. Wasn't it so much easier just to type it into that?
Yes.
Okay. We've got this same parabola, opens down with a vertex of 0, 2.